What is nanolithography? The term nanolithography refers to the fabrication of structure at the nanometric scale, meaning patterns with at least one dimension ranging between 0.1 nanometers and 100 nanometers. These techniques are widely used in the semiconductor industry, but can also be applied to numerous other fields. To achieve such a small-scale pattern, several techniques can be employed, including optical lithography, X-ray lithography, electron beam lithography, extreme ultraviolet lithography, natural particle lithography, and more. Among these, some techniques make use of atomic force microscope. This instrument is particularly interesting. This tip is typically made of silicon or silicon nitride and has a curvature radius in the nanometer range. Through the interactions between the tip and the substrate, we can not only characterize the molecular top layer of the surface, extracting information about parameters such as adhesion, conductivity, three-dimensional arrangement and the nature of surface molecules, but also modify the sample surface with extreme precision. This approach enables the technique known as scanning probe lithography.
The main techniques of scanning probe lithography, SPL, can be categorized into two groups. Destructive SPL, which involves the removal of material from the surface. Constructive SPL, which involves the deposition of material onto the surface. The former group utilizes various physical interactions, e.g., electric potential, heat, applied force, etc., between the probe and the surface to ablate or modify existing materials. For example, mechanical scanning, probe lithography, MSPL, is the most basic form of SPL, in which the direct application of force by the probe induces the removal of material from a surface. The process results in nanoscale writing. Thermochemical scanning probe lithography, TCSPL, employs a heated probe to initiate a localized, thermally driven chemical reaction. Electrochemical scanning probe lithography, electrochemical SPL, enables a reaction to occur within an in situ generated electrochemical cell, where the probe and the surface act as electrodes, and a water meniscus formed between them serves as the electrolyte. The key parameters governing the local electrochemical process and the resolution of the nanopatterns are the voltage applied between the probe tip and the surface, the scanning speed of the tip, and the relative humidity of the surrounding atmosphere. In constructive techniques, the probe is used to deposit molecules onto the surface in a spatially controlled manner. Dip pen nanolithography, DPN, utilizes a water meniscus that forms at the contact point between the tip and the surface to enable capillary transport of small molecules. Molecular transport is influenced by relative humidity, contact time, temperature, and the physico-chemical properties of both the ink and the substrate. Polymer pen lithography, PPL, combines the advantages of multi-tip DPN with the simplicity, cost-effectiveness, and robustness of microcontact printing. The deformability of PPL probes allows the modulation of the printed feature properties through the amount of force applied by the probes. This technique has been employed to covalently print and bind functionalized cyclopentadienes onto graphene via a Diels-Alder reaction, demonstrating the capability to drive chemical reactions through mechanical force. The techniques discussed represent only a subset of the versatile array of methods available for the nanoscale fabrication and modification of materials, opening new possibilities for device design and the manipulation of material properties.
Nevertheless, the convenience of being able to characterize, analyze, and modify surfaces using a single instrument makes atomic force microscope a truly unique tool.
Thank you for your attention.